Next up is how do we deal with the derivative of a power function that also has a coefficient? So far, we know that the derivative of a power function, we can drop the power and subtract 1 to it in order to find the derivative of such a function. And we also know that the derivative of a constant is 0. But what if we have some combination of product of a constant with something like 7 times x squared? Well, we could always examine what would happen the long way, basically by checking out what will happen based on the difference quotient. But this lecture series is getting quite long, so I'll go ahead and leave this to you as an exercise. Try by difference quotient. What you will get here is the derivative of this will be equal to 14x. And basically, if we were to apply the power rule, basically what you can do is you can take the power rule of the x part of this term of this applies to polynomials as well. Basically, what will happen is the 2 will drop down, as we did in the last couple videos for the power rule. This 2 will drop down as a multiplier. Since that's 7 times x squared, the derivative of x squared is 2x. And so what I get is 7 times 2x, the derivative of x squared. And what I'd be left with is 14x. But basically, there's an underlying principle here that is, what if I have a derivative of a coefficient times a function? What if there's a number out front multiplying by the function? How does that work? And basically, the short answer here is it's always equal to c times the derivative of the function, meaning that that coefficient will not affect the derivative. I can take the derivative of x squared completely by itself, which would be 2x, and then multiply by the 7 afterwards to get my derivative. And again, you can check the difference quotient here in order to do this. Now, the proof of this rule is quite simple. We can actually do it generically using the difference quotient. Let's go ahead and do that. And I'll remind you guys that proofs is not something that you need to worry about, but it's helpful to see the algebraic logic of why it works in a generalistic sense. But let's let f of x be equal to c times f of x. Now, if we wanted to find the derivative of f of x, again, we'll just call that capital F prime, we would need to find what's the limit as h approaches 0 of capital F of x minus capital F of x plus h minus capital F of x divided by h. And basically, since capital F of x is equal to c f of x, this would be equal to the limit, and again, we would say this is equal to f prime of x here. This would be equal to the limit as h approaches 0 of, well, capital F is just equal to c f of x. So this would be c times f of x plus h. And then capital F of x is equal to c times f of x. So that would be minus capital F of x, which is c little f of x. And again, those would be multiplied. And this would all be divided by h. Well, notice here that c is a common factor in the numerator. I could factor that out from this horrible looking numerator on the difference quotient here, like so. And by limit law number 6, remember that the limit, if I have a limit of a constant value that does not have to do with h in this case, I can pull that limit through. So this would be equal to c times the limit. So limit law number 6. Basically, we can use limit laws to help figure out rules for derivatives, and that's essentially what I'm saying here. But this would leave me with f of x plus h minus f of x. And the rest of this stuff I cannot pull through the limit because all of this involves h. So, but I could pull that c through because it did not have to do with the h. And what you'll notice here is, well, this is just the difference quotient of the function little f of x. So, and again, by definition, that is just f prime of x. And so what I've just done is I've proved this exact rule, that if I want to find the derivative of a function which is defined to be c times f of x, that's always equal to c times the derivative of the function on the inside. That's exactly what this rule is saying right here, that, if I want the derivative of a number times f of x, that's just equal to the number times its derivative. So let's do a couple examples and wrap this video up, because so far I've been very abstract talking about proofs and so on, but basically if I want to use this rule, how do I do it? But basically, if I want to solve the derivative of 4x to the 5th, I could use this rule and pull the 4 out front. This 4 will not affect the derivative of the function of the x component. Essentially, you can pull a number multiplier through a derivative and use it outside. And again, what this would mean is this times the derivative of x to the 5th. Now I know the derivative of this by simply the power rule, and that would leave me with 4 times 5x to the 4th. Because again, to find the derivative of x to the 5th, I drop the power, subtract 1. And there I would have that. And now what I could say is, well, 4 times 5 is, of course, going to be 20 x to the 4th, and this would give me my derivative. Or a shortcut that you could remember, which is a lot easier for such polynomials, is when you're dropping the 5 down, that will just multiply into the 4, leave me with 20. Again, as long as I remember to subtract 1, I'm good to go. I've got my derivative. In the next video, we will finish the rest of the examples by extending this.